Your refrigerator is not protecting your food. It is quietly helping bacteria survive. Every time you close that door, you think you've slowed spoilage, but the reality is colder, harsher, and a lot more dangerous than most people ever realize. Up to 100% of home refrigerators test positive for active bacterial contamination. And every cooling cycle pushes that contamination through the air, across every surface, and onto everything you plan to eat. You're not just storing leftovers, you're surrounding them with microbes that never stop growing, only slow down just enough to go unnoticed. And here's the part that should concern you the most. The materials inside your fridge, plastic and stainless steel, do absolutely nothing to fight it. They don't kill bacteria, they don't resist it. They don't even slow it down further. They just sit there while everything spreads. So the real question isn't why your food spoils, it's why you were told this system works in the first place. Because there is a simple, overlooked fix that changes this entire environment. And once you understand it, you won't trust your fridge the same way again. Because here's what's actually happening inside your refrigerator. And once you see it, it's hard to unsee cold does not kill bacteria. It never did. It only slows their metabolism, like putting them into a low-power state where they keep functioning, just more quietly. There's an entire class of microorganisms, psychotrophic bacteria, that are specifically adapted to thrive in cold environments, including common strains like Pseudomonas and Listeria. They don't just survive your fridge, they're built for it. And while you assume everything is safely isolated on separate shelves, your refrigerator is constantly moving air through a circulation system designed to maintain temperature. That airflow doesn't just carry cold, it carries microscopic life from one surface to another. From raw food to cooked food, from one container to everything else you own. Every time the fan kicks on, you're not preserving your food, you're redistributing bacteria across it. What started on a single piece of produce doesn't stay there. It becomes part of the entire environment. And because nothing inside your fridge is actively fighting back, those microbes settle, attach, and slowly multiply in places you never think to check. So the problem isn't just that bacteria exist, it's that your fridge is quietly helping them spread. And that's where everything starts to change. And that's where a completely different kind of mechanism enters the picture, one that doesn't rely on temperature, chemicals, or timing, but on something far more fundamental. Copper works through what's known as the oligodynamic effect, a process where metal ions actively destroy microorganisms on contact. When copper is exposed to air and even minimal moisture, it begins releasing positively charged ions that interact directly with bacterial cells. Those ions penetrate the cell membrane, disrupt critical proteins, and interfere with the cell's ability to produce energy. At the same time, they trigger internal oxidative stress, similar to how your immune system attacks pathogens, leading to rapid structural damage from the inside out. What makes this different from most antimicrobial methods is that it's not biological in the way bacteria can adapt to. Antibiotics target specific pathways, which is why resistance develops. Heat kills through extreme conditions, but only when consistently applied. Copper, on the other hand, operates through a continuous electrochemical process. There's no on or off, no dosage to manage, and no adaptation curve for bacteria to climb. You can't evolve your way around a metal ion. Breaking your cell structure apart, it's a physical limitation, not a biological challenge. And because this reaction happens at the surface level, it doesn't need complex systems or high-energy input to function. The moment bacteria make contact with copper or even exist in its immediate environment, they're exposed to a process that steadily degrades their ability to survive. No waiting, no buildup, no threshold effect. Just a constant, low-level pressure that bacteria simply aren't equipped to handle. And once you understand that difference, the limitations of your refrigerator start to become very clear. Now, picture what actually happens the moment a bacterium encounters copper, not as an abstract concept, but as a sequence you can almost see unfolding in real time. A single cell lands on the surface, intact, active, still functioning, and within seconds, that stability starts to collapse. Copper ions begin to attach to the outer membrane, creating tiny breaches that the cell cannot seal. What looked like a solid barrier turns porous when stably exposed. The interior chemistry shifts immediately. Energy production falters, enzymes misfire, And the system that keeps the cell alive starts breaking down from multiple directions at once. Then it escalates inside the cell. Reactive oxygen species begin to form highly destructive molecules that attack proteins, lipids, and DNA simultaneously. It's not a single point of failure. It's a cascade. The bacterium isn't being killed in one clean step. It's being overwhelmed, piece by piece, faster than it can respond. Its DNA fragments, its structural integrity weakens, and the internal pressure builds until the membrane can no longer hold. What was once a functioning organism becomes unstable debris in a matter of minutes under the right conditions. And here's what makes this moment so different from anything happening in your refrigerator. Cold slows bacteria, but it leaves them intact. Copper doesn't slow them, it dismantles them. One environment preserves structure, the other actively destroys it. And when you visualize that contrast, one system quietly maintaining life, the other systematically breaking it apart, you start to see why this changes everything. And this isn't just theory or a clever explanation, it's been tested in environments where failure has real consequences. In controlled clinical trials, hospitals replaced standard high-touch surfaces like bed rails, garde pole, and call buttons with copper alloys, and the results were immediate and measurable. Hospital-acquired infections dropped by 58%, not because protocols changed, not because staff behavior improved, but because the material itself was actively reducing the microbial load around patients. That's a structural advantage, not a temporary fix. At the laboratory level, the data is even more precise. Under standardized testing conditions, copper surfaces have been shown to eliminate more than 99% of dangerous bacteria within 2 hours, including strains like MRSA and E. coli that are known for persistence and resistance. And unlike chemical disinfectants, this effect doesn't wear off or require reapplication. It continues as long as the surface exists. This is why in 2008, the Environmental Protection Agency officially registered copper alloys as the first solid surface material allowed to make public health claims for continuously killing bacteria, not reducing, not slowing killing on contact over time without interruption. So when you step back and look at that level of validation, the question shifts again. If the evidence is this clear, then why isn't this already everywhere? And this is the moment where the logic should snap into place. If this works this well, why isn't it already everywhere? Why are the surfaces in your kitchen, your refrigerator, even critical spaces like hospitals, still dominated by materials that do nothing to stop bacterial growth? The answer isn't science, it's economics and manufacturing reality. Stainless steel and plastic didn't win because they're better at protecting you. They won because they're cheaper, easier to produce at scale, and visually associated with cleanliness. They look sterile, they feel modern, and they fit the industrial pipeline that keeps costs predictable. Switching entire systems to copper isn't a small upgrade, it's a massive capital shift. It means redesigning production lines, retooling supply chains, and accepting higher material costs across millions of units. So instead of choosing what actively reduces risk, industries often choose what maintains efficiency. And over time, that choice becomes invisible, normalized to the point where nobody questions it anymore. But once you see the difference, one material that passively allows bacteria to persist and another that actively breaks it down, you start to realize something uncomfortable. You weren't given the best solution, you were given the most practical one. And those two are not the same. So I decided to stop guessing and actually test it, not in a lab, not under controlled conditions, but in the exact environment you use every single day. I took 2 identical sets of food, same strawberries, same leftovers, same containers, and placed one set in a standard refrigerator setup, and the other with a simple piece of copper mesh positioned near the airflow. Nothing else changed. Same temperature, around 37 degrees Fahrenheit, same shelf, same timing. By day 3, there was no obvious difference. Everything still looked fine, and honestly, that's where most people would stop and assume nothing's happened. But by day 5, something subtle started to shift. The control side, the one without copper, had that faint early-stage softness in the fruit, the kind you don't notice until it's too late. The leftovers had just a slight change in smell, not bad yet, but not as clean. And then day 7 hit, and the difference wasn't subtle anymore. The side without copper had visible breakdown moisture buildup, texture loss, early spoilage. The side with copper, still holding structure, still smelling fresh, still usable, not perfect, not magically preserved, but noticeably delayed in a way that caught me off guard. And that's when it clicked. This wasn't about stopping time. It was about changing the environment just enough to shift the outcome. And once you see that shift, the next question becomes obvious. How does something so small create that kind of change without even touching your food? The answer comes back to how your refrigerator actually works as a system. It's not a static box. It's a controlled airflow environment. Cold air is constantly pulled, cooled, and pushed back through vents to keep the temperature stable, which means everything inside is connected by that moving air. When you introduce copper into that space, you're not trying to coat every surface or wrap every item, you're placing it directly into the pathway where that air circulates. As air passes over the copper, it carries fewer viable microbes with it, lowering the overall bacterial load moving through the entire fridge. That doesn't require direct contact with every piece of food because the environment itself is being altered at a baseline level. Think of it less like a shield around individual items and more like a filter affecting the conditions they all exist in. You're not protecting one container, you're influencing everything that shares that airflow. And once the environment shifts, even slightly, the rate at which bacteria spread and settle begins to change. That's the bridge between theory and reality. You don't need full coverage. You just need strategic placement inside a system that's already doing the distribution for you. So here's exactly how you do it. Step by step, with nothing complicated and nothing expensive. Go to any hardware store or even the cleaning aisle at a grocery store and look for 100% pure copper mesh, usually sold as a scrubber. Not copper-coated, not mixed metal, you want solid copper. A 3-pack typically costs around $4 to $6. Once you have it, don't overthink the setup. Loosely coil one piece so it has as much exposed surface area as possible. Don't compress it into a tight ball. Surface area is what drives the ion release. Now open your refrigerator and locate the airflow path inmost you. Yes, models. That's near the back wall where you feel a faint stream of cold air coming from a vent. Place the copper mesh on a shelf close to that vent, not touching food, not blocking airflow, just sitting in the path where air moves naturally. That's it. No tools, no mounting, no power source. Close the door and let the system do the work. You're not installing a device, you're introducing a material that passively changes the environment every time the fan cycles. Leave it there. Don't rinse it. Don't replace it weekly. Let it operate continuously. Simple, low cost, and once it's in place, it never turns off. Before you run off and expect this to turn your refrigerator into a sterile lab, let's be clear about what this is and what it isn't. Copper is not a magic switch that eliminates every microbe overnight. It doesn't replace proper food storage. It doesn't fix temperature issues. And it won't stop spoilage completely. What it does, and this is the part that matters, is change the baseline environment in a way your current setup never could. Instead of bacteria moving freely through a passive system, they're now constantly exposed to a low-level, continuous stress that interferes with their ability to survive and spread. It's not about perfection, it's about pressure. Even a modest reduction in microbial load can translate into noticeably slower spoilage, cleaner surfaces, and more stability over time. And that distinction is important because it keeps expectations grounded in reality. You're not freezing time, you're shifting the math. You're taking an environment that does nothing to fight back and introducing something that does quietly, consistently, and without maintenance. That's why the results feel subtle at first, then become more obvious over days, not minutes. So don't think of this as a miracle fix. Think of it as a smarter baseline, one that gives your food a better chance. Every single day, it sits inside your fridge. And over time, you're going to notice something that might seem like a problem at first, but it's actually the opposite. That bright, shiny copper you placed in your fridge will start to darken, turning brown or even greenish as it develops a natural patina. Most people assume that means it's wearing out or losing effectiveness. It's not. That surface change is a direct result of oxidation, the same process that allows copper to release ions in the first place. In fact, Studies have shown that tarnished copper can be just as effective, and in some cases even more active, than freshly polished copper. The oxidized layer increases surface complexity, which can enhance ion interaction with microbes. So what looks like decay is actually activation. You're not watching it degrade, you're watching it work. And that's the moment most people miss, because we're conditioned to associate clean with shiny. But in this case, the darker it gets, the more it's been doing its job all along. And once you understand how this works, it's hard not to see the same pattern everywhere you live. The refrigerator was just the beginning. Start paying attention to the surfaces you touch every single day, the ones that quietly collect bacteria without ever doing anything to fight it. Door handles, light switches, cabinet pulls, faux serveurs. These are high contact zones, constantly exposed, rarely disinfected, and almost always made from materials that are completely passive. Now imagine replacing just a few of those with copper-based alternatives: solid brass door handles, copper switch plates, even small copper elements placed near high-traffic areas. You're not redesigning your entire home. You're strategically upgrading the points where bacteria accumulate the most. And just like inside your refrigerator, the effect isn't limited to direct contact. As these surfaces interact with the environment, they begin to reduce the microbial load around them in subtle but measurable ways. It's not about turning your home into a sterile space, it's about introducing active surfaces into places that have always been inactive. And once you see how a simple material can shift the conditions of an entire system, you start to realize this isn't a one-use idea. It's a framework you can apply anywhere contact and contamination overlap, and just when it feels like the effect should be limited to where copper actually sits. This is where it takes an unexpected turn. Copper doesn't just protect the surface it touches, it influences the space around it. Researchers have observed what's often called a halo effect, where nearby non-copper surfaces show significantly lower bacterial contamination simply because they're within the immediate environment of copper. No direct contact, no coating, just proximity. That happens because the same ions and microinteractions that disrupt bacteria on copper surfaces begin to affect the surrounding zone at a lower intensity. You're not just changing one point, you're shifting the microbial pressure across an entire area. In a refrigerator, that means items sitting inches away can benefit without ever touching the copper itself. In your home, it means high contact zones can indirectly influence adjacent surfaces. It's a small detail, but it changes how you think about placement. You're not just adding copper, you're creating a field of influence. And once you step back, this stops feeling like a new discovery and starts looking like something we simply forgot. Ancient civilizations were already using copper long before modern science explained why it worked. In ancient Egypt, water was stored in copper vessels because people noticed it stayed fresher, longer, without spoiling as quickly. They didn't have microbiology. They had observation, and the results were consistent enough to become routine. The Romans took it further, integrating copper into their water systems and even using copper-based compounds in medical treatments to reduce infection across different cultures and continents. The same pattern kept appearing when copper was involved. Contamination dropped, even in traditional practices, from early Ayurvedic methods to old world kitchens. Copper surfaces were trusted in ways that modern materials replaced but never truly improved upon. They didn't call it antimicrobial, they just knew it worked. And now, thousands of years later, science is finally explaining what those systems were already proving in real life. When you put it all together, the difference becomes almost impossible to ignore. Before, your refrigerator was a passive environment, cold, controlled, but ultimately doing nothing to stop what was already there. After introducing copper, that same space becomes active, applying continuous pressure that bacteria can't easily withstand. You didn't change the temperature, you didn't change the system, you changed the conditions inside it. And that shift, even at a small level, compounds over time into something you can actually see, smell, and experience. And that brings you back to where we started. Your refrigerator never truly stopped bacteria, it only slowed them down. Now, you've introduced something that does more than delay. It disrupts. It challenges the entire environment in a way your fridge never could on its own. And once you understand that, it's hard to go back to doing nothing. A fewer dollar change, sitting quietly on a shelf, altering the outcome every single day. If this made you see your kitchen differently, share it with someone who still thinks cold means clean.